Good afternoon, everybody. How is your energy level going? How is your energy bar? Is it full? Are you excited for the weekend? I am excited for the weekend. So let's finish this. At least let's finish the black hole astrophysics lectures. And today we will finish the topic of outflows from black holes and cover the phenomenology, some of the interesting phenomenology about the, in other words, the observational manifestation, a global overview of the observational manifestation of black holes in the electromagnetic spectrum. So yesterday we finished the lecture with these beautiful images of jets, most of them relativistic, from active galactic nuclei that we will learn more about active galactic nuclei today. Black hole binaries, young stellar objects. In other words, there is a young star with a protoplanetary disk and you get a jet because you have all the ingredients for getting a jet here except relativistic space-time. So you get a jet, but the jet is not very powerful. Tidal disruption events and gamma ray bursts. Jets are very important because they seem to, from the 1 n equal 1 data point we have so far, it seems that jets like to go along with gravitational wave emission. In fact, if the gamma ray burst model is correct, then we should expect a lot of gravitational wave detections in the future together with electromagnetic radiation from jets. So now that we had a broad view of how you can get a jet out of a black hole. In other words, you need rotation, okay? You need a magnetic field, a large magnetic field, okay? And you need to you need accretion. In other words, you need to bring this field onto the central object. Now that we learned the basic tenets of this model, let's apply this simple picture of jet production to different systems. Beginning with black holes located in the centers of galaxies and binary systems in our galaxy, for instance. So it turns out that at the bottom of the gravitational potential at the center of a galaxy, where you have supermassive black holes, you have a lot of gas available, magnetized gas, bringing magnetic fields down to the black hole. And these black holes, we think they should be spinning. We are not sure how fast they are spinning, but they should be spinning to some degree. We lack good measurements of the spin parameter for black holes in general. And we also have this condition in binary systems where there is a donor star giving material to the more massive black hole of the system. And in my group, we have been playing this game of trying to understand how this occurs in practice. So here what you see, what I will show you is a numerical simulation of what it should look like to be a black hole at the center of a galaxy or a black hole in a binary system where you provide gas to the black hole. So here I will show you a numerical simulation of black hole accretion giving rise to a relativistic jet. So what you will see here on the on the right side, you are seeing the logarithm of the gas density, okay? The black lines are the poloidal component of the magnetic field. And now what I will start solving the conservation equations of general relativistic magnetohydrodynamics. And we used an open source code to do this. This simulation was performed by my PhD student, Gustavo Soares, who is now visiting Northwestern University. And let's see, so the black hole is almost invisible here. The black hole is the tiny little circle here. It's rapidly spinning. The spin parameter here is, if I'm not mistaken, 0.93. So let's see what happens here. So what happens is you get the magnet. Let me repeat this because this goes very fast. The time scale here in geometrized units. So as soon as we start the simulation, also pay attention that we start with a nice torus of gas, a nice donut of gas around the black hole. So we start the simulation, magnetorotational instability removes angular momentum from the inner parts of the disk. The gas accretion proceeds. The gas falls into the event horizon, bringing together the magnetic field. The magnetic field spirals around the event horizon because it's spinning, okay? So you have the conditions for a Blandford-Snarek powered relativistic jet, and you start forming the typical conditions that you expect of the Blandford-Snarek process. You have this magnetic hair threading the event horizon of the black hole, and you also get a highly turbulent accretion disk around the black hole. So you have a Poynting flux dominated jet which is producing electromagnetic radiation which is flowing around the polar funnel here, and eventually this radiation will be transferred to radiating particles. This electromagnetic energy will be transferred channel to light. You have also subrelativistic winds, and you also have the body of the accretion disk here. We didn't run for a terribly long time this simulation, but Ivan, who is sitting, he loves to sit in the back of the room. He's running a more simple, a Newtonian version of the simulation for, I think, 100 times longer, right, Ivan? Is it 200,000 M you ran your simulation? 100,000. Anyway, we can, I don't remember, we can talk later. Okay, so this is how you get this. We think that something similar to this is happening at the centers of galaxies and in binary systems. And if you zoom in closer to the black hole, things start getting more rapid, okay? This is a zoomed in version of the same kind of simulation. This was performed by John McKinney. And you see the typical properties of the Blandford-Snarek configuration now in a real astrophysical scenario, not the time model I showed you yesterday. You see that the field lines, they are oscillating with some characteristic frequency. They produce what we call a quasi-periodic oscillation, which will be the topic of the project of Roberta, who is sitting in the back of the room. So the magnetic fields are dancing a little bit. So this is very interesting. We think that something similar to this we actually find at the centers of many galaxies. As I will talk very soon. So not only you can get jets from isolated black holes where you feed gas and you feed magnetic fields to these black holes, but we think that when a star dies, you also get conditions appropriate for producing a relativistic jet. So this is how it goes. Imagine you have a rotating massive star, and when I say massive, I say a star with a mass larger than 30, around 30 solar masses. At some point in the life of this star, it will deplete the fuel, the nuclear fusion, the supply for nuclear burning inside the star, and it will lose pressure support from this from the heat produced in the nuclear reactions, and you will have and then it will collapse. Okay, the core collapses. Nothing can prevent the gravitational collapse of the star, and it's spinning, and it has an internal magnetic field which was generated by dynamo processes. It's a way that you can amplify magnetic fields in physics. It's called dynamo process. So it will have a core collapse, as we say in astrophysics, and at some point it will have enough mass collapsing to the center of the star, and it will eventually produce an event horizon. It will produce a black hole, an accreting curved black hole, and here the accreting material is the remains of the star itself, which will feed the newborn baby black hole. And what will happen here, something that is very interesting, is that you have rotation, okay, because you have the residual the angular momentum of the star, okay. You have the magnetic fields because the star is magnetized. And you have accretion. The accretion is being provided by the own gravitational collapse of the initial star, because at some point it doesn't have pressure support anymore. And we think that the resulting accretion rates here are way over the Eddington accretion rate that we defined 2 lectures ago. And we think that this is it's a very interesting system where you can get a very powerful Blandford-Najac jet being produced, the astrophysical Penrose process here happening. So what we think is that the new black hole will produce this extremely relativistic jet with Lorentz factors way above the Lorentz factors you can get. The Lorentz factors you can get out of this process. Sometimes they approach 1,000. So it's relativistic. And in the star, and it will propagate into the interstellar medium outside the star. The energetics of the jet are incredible. The efficiency of converting the rest mass energy into Poynting flux of the jet, they are really incredible. If you are an observer that is sitting at the axis of this star, if you are an observer sitting at the axis of the star, you will observe severe aberration and beaming of the jet because of the relativistic motion of these particles. And the duration of this process, the duration of the jet production is thought, you can do some order of magnitude estimates. One order of magnitude estimate is the free fall time scale of particles at the surface of the initial star. And you expect that the duration of the jet production will last a couple of seconds before the material is depleted and completely accreted inside the black hole. And as I will explain later, we think that we call this collapser scenario, and we think this gives rise to jets that we observe in the long duration gamma ray bursts. Another way of getting a relativistic jet is when you have binary systems where you have, I will give up using this laser because it's not working, so please follow my explanation. In systems where you have 2 neutron stars orbiting each other, therefore emitting gravitational waves, losing orbital energy, and eventually they will coalesce, or a system where you have 1 neutron star and 1 black hole. Okay, as you are learning, the system loses the energy. Eventually, the system coalesces, and at some point, we expect that you might have, for some amount of time, a high mass neutron star, which eventually decays into a stellar mass black hole. And the interesting thing here is that again, because as we know, neutron stars have very strong magnetic fields. It will provide a lot of magnetic field to the newborn black hole. The accretion, the material is reaching neutrons now. The accretion disk is really reaching neutrons. And you will eventually get a relativistic jet out of this system. And this is nothing new. This scenario was proposed 30 years ago. Okay, and we think this is the scenario for the so-called short duration gamma ray bursts. The duration of the system here is supposed to be of the order of milliseconds, the duration of the jet production phenomena. And nowadays there are people that are doing numerical, they are solving Einstein's equation, they are evolving the space-time of the coalescent system together with the fluid equations of the system to try, and the magnetic fields to try to on here. So this is a simulation by the group of Luciano Rezzolla together with Bruno Comazzo, where they take 2 neutron stars. They use some equation of state to model the interiors of the neutron stars. They evolve the system. So on the left side, you're seeing the gas density. On the right side, you're seeing the magnetic field strength. And after they evolve the system for some in the systems, the time during which they evolve the system corresponds to about, I think, 50 milliseconds or something like that. And at the end, they get some nice pure jet that is produced as a result of the coalescence of the two neutron stars. The initially chaotic magnetic field gets ordered by the spin of the black hole, produces a helicoidal tower characteristic of the Blandford-Snellius process, and you get a short gamma ray burst jet in the end. The simulated jet is looking like kinds of jets that we observe in gamma ray bursts, but there is a long way to go here. Okay, I will not give you the director's cut, and I will proceed now to talk about observed black holes. In other words, let's apply the broad picture we saw of the theory, and now let's have a broad picture of observations of black holes, astrophysical black holes, in the electromagnetic spectrum. So we have two populations of black holes. We think we have essentially two populations of black holes in the universe. The first population is what we call the supermassive black holes. So supermassive black holes are black holes with masses between 1 million to 10 billion solar masses inside the event horizon. We think that there is one supermassive black hole at the center of every evolved galaxy. Sometimes there is a quest for binary supermassive black holes at the centers of galaxies, which we expect from, if the universe works according to standard cosmology and the lambda CDM scenario, we expect to see lots of binary black holes, merging black holes at the centers of galaxies. This is an outstanding problem in astrophysics, which I hope Lisa will help us in 20 or 30 years. And another kind of black hole are the so-called stellar mass black holes. So stellar mass black holes are black holes which are millions, billions of times less massive than the supermassive ones. They have masses between a couple of solar masses to up to, now I have to update this slide, but the latest LIGO measurement, they estimated an 80 solar masses black hole, was it? The discovery, I don't remember now, but I think I have to update this slide. But they can go up to a couple dozens of solar masses. And in our galaxy alone, we think that there are more than 1 million stellar mass black holes. In our galaxy, imagine if you integrate all galaxies in the universe. And the reasoning behind this estimate is we use models for stellar evolution, and there are lots of massive stars. They are massive enough to end their lives as stellar mass black holes in our galaxy. So that's how we end up at this number of 10 to the 7 stellar mass black holes in our galaxy alone. This is what the stellar mass black holes that we have found so far, they look like. We think that they are usually in binary systems. They interact gravitationally with other stars. They get caught in binary systems with this gravitational scattering processes. And usually there is a less massive star orbiting the more massive compact object. And the black hole, sometimes you also have a neutron star material, and we observe a very interesting and complex phenomenology for these systems. And usually they are very bright in the X-ray part of the electromagnetic spectrum, essentially because of the physics of the black body emission of the accretion disk. For this mass, you can estimate that they should be shining very brightly in X-rays, so we call them X-ray binaries. As you know, we have also the binary systems that were found with LIGO. Oh, there is sound effects. Sasha showed you this movie yesterday. So we have lots of binary systems made only of space-time, apparently no barrier, no gas polluting these systems, so no electromagnetic emission. And so this will become this is becoming an important business, and I think that very soon the number of binary systems found with LIGO and Virgo will exceed the number of X-ray binaries very soon, I think, maybe even in the middle of next year. And here is some gentle supermassive black holes they look like at the centers of some inactive galaxies. Well, not all, actually all of these galaxies are active, they are weakly active. So at the center, this is what you are seeing here is a combination of X-ray and optical observations of 4 different galaxies, including this one which is called Sombrero. You can imagine why the upper one is called Sombrero, right? As you can, it looks like a sombrero. So the galaxy on the upper left part of this image is weakly active. M81 here on the lower left corner is also weakly active. Actually, all of the galaxies here they have weakly accreting black holes. They emit radiation. The accreting black hole emits radiation all across the electromagnetic spectrum. And there is one outstanding question in astrophysics, which is, what about dwarf galaxies? What about proto-galaxies? What about the black holes? How in the history of the universe, how in cosmology can you provide so much massive to create a black hole with billion solar masses inside the event horizon? Well, is it possible? I mean, it is possible because we measure such masses, but how to understand the cosmological evolution of these black holes and the seeds of supermassive black holes? This is an outstanding question in astrophysics. So here is how it goes for what we call the active galactic nuclei. You have a nice galaxy, you have a supermassive black hole at the center of the galaxy. Something happens and removes angular momentum from the body of the galaxy, dragging the gas to the center of mass of the galaxy, feeding the central supermassive black hole with gas and therefore producing a radiating accretion disk and sometimes a jet. And when you have an active black hole, actively accreting material, we call an active galactic nuclei, and we abbreviation AGN. Okay, active galaxy. The galaxy is activated when its central black hole is provided with a lot of gas. Now, I will use now the AGN acronym several times now during the rest of the lecture. But before diving into AGNs, let's have a look at the nearest supermassive black hole, which is located at the center of our own galaxy, Sagittarius A star, it's its name. Sagittarius because it's located at the center of our galaxy. It's located at the direction of the Sagittarius constellation. But as you know, constellations are absolutely worthless and have no physical meaning. And this is a mock picture of our galaxy. We cannot really take a selfie of our galaxy. Okay, we will need a really large selfie stick to take a selfie of our galaxy, so that's not possible. Oops. Yeah, so Sagittarius A star, the central supermassive black hole, is located at the center of the bulge of our galaxy, and the solar system is in a forgotten corner of the galaxy. We are absolutely not special in the universe, as you probably know. And now what I would like to show you is a combination of several different observations where we will take a part of the sky pointing in the direction of Sagittarius A star, and we will zoom in progressively with higher levels of zoom on, and look at, and finally going to the black hole at the center of the galaxy. So first we start at the Paranal site of the European Southern Observatory. This is what it will look like here at the surface of the planet, looking at the center of the galaxy. I think Sagittarius is the Scorpion. I'm not really good with constellations, but I think Sagittarius is the Scorpion constellation. I know nothing. I think Sagittarius means Scorpion in Latin, right? Or Greek or something. Nobody knows anything? No? Nobody speaks Greek or Latin here? No? Okay, good for you. Okay, so let's progressively zoom in to the center of our galaxy. So now we are crossing through the very dusty parts of the disk of our galaxy, getting inside the bulge. You see the many millions of stars at the bulge of our galaxy. Now we are getting progressively towards the center of mass of the galaxy. There are less stars, and as you can see, and now we are really approaching the region of gravitational influence of the central black hole, Sagittarius A star, with a mass of 4 million solar masses. And in order to go around the dusty emission that pollutes our observations, you have to use a technique called adaptive optics, looking at the near infrared wavelengths. And what you see with adaptive optics is this very weird picture. This is actually a movie made out of dozens of observations over the last 20 years with Keck. And what you're seeing here is the near infrared emission of stars circling around the invisible center, almost invisible center of mass of our galaxy. And what you can do here, you can play a game which is you can apply Kepler's laws to the orbit of these blobs, which are really stars. And you can estimate, you can measure the size of the orbit, the semi-major axis of the orbits of the stars, and you can measure the periods of the orbits, and you can constrain the mass. And that's how you estimate that the mass of the central black hole is 4 million solar masses. So how do we know? What is the recipe for trying to find, and locate black holes through their electromagnetic radiation in the universe? What are the observational signatures of black holes in the universe? The first sign that you might be observing the manifestation of a black hole is you need to measure the mass of the black hole, and you need to measure some estimate of the size of the system, okay? So if you have evidence to think that your system is compact and it's too massive to be in the form of a neutron star, then you are probably dealing with a black hole, okay? So you need, of course, mass and size measurements, and there are several different ways of measuring mass and several different ways of estimating the size of a system with electromagnetic telescopes. The definite proof of a black hole will be to observe the membrane, the event horizon of the black hole. Right now, it's not possible to observe an event horizon, but very soon with the Event Horizon Telescope, we might catch the shadows of at least probably 2 event horizons at the centers of galaxies. So let's talk a little bit about how to measure mass in astronomy. Okay, this is a very important concept. You don't need to be located at the system to estimate the mass of the system. And the way you do it, and this is actually the way you define mass in general relativity, right? You define mass by its effects on test particles. And the idea is if you observe the electromagnetic radiation of test particles around some central mass, okay, it should be, if it's rotating around if it's orbiting around the central mass, it should follow a Keplerian orbit. And you can very easily demonstrate that this is what we call the rotation curve of the Keplerian velocity, the relation between the orbital velocity, the mass, and the size of the orbit. So you can then measure the mass by measuring the size of the orbit, speed of the particles. Or you can alternatively use Kepler's third law, and you can estimate the mass if you are seeing the electromagnetic radiation of test particles around a central object. Astronomers have been playing this game for many decades now in using Kepler's laws to estimate masses of astronomical systems. And that's how we first have had strong evidence that we were dealing with black holes. When you have an X-ray binary, you use the the companion star, and you see the motion of the star through the Doppler shifting of the radiation, and you can then use Kepler's law, apply it to the modulation of the observations because of the motion of the less massive star around the more compact, more massive object, and you can estimate, that's how we estimate massive black holes in X-ray binaries. Essentially, if you get a mass over 2 solar masses, the more massive object is probably a stellar mass black hole. This is a histogram. This is a probability distribution plot of masses estimated from, on the right side, from stellar mass black holes in X-ray binary systems, and on the left side, masses estimated for neutron stars. And you can see this very nice result that the neutron star masses, they are usually below 2 solar masses. So this seems to go in the direction of the estimates for the limiting mass of a neutron star of around 2 solar masses, supported by Fermi pressure of neutrons. And this plot needs, of course, to be updated with the masses of the LIGO, Virgo black hole binary systems. Okay, so I talked about Keplerian motion. Another way that you can probe the mass of black holes is, again, suppose you have gas orbiting. Imagine that the red particles, they are gas particles orbiting around some central object. And you are able, using different techniques, let's say Doppler shifting of the electromagnetic radiation, to build what we call the rotation curve, a curve relating the velocity of the gas with the distance of the gas to the center of the orbital motion. This is the characteristic curve of Keplerian motion. So if you observe this kind of curve, it means you have test particles orbiting some much more massive central object, and you can immediately estimate the mass of the central object. So again, astronomers have been playing this game for a couple of decades using Hubble Space Telescope. This was one of the major contributions of Hubble Space Telescope. So what you're seeing on the right, on the left, are Hubble HST observations of ionized gas at the center of the giant elliptical galaxy M87. And you are able to derive the rotation curve of the ionized gas around the center of mass of the galaxy. And what you see is Keplerian motion. This is a beautiful result from the late 90s, where you see this beautiful Keplerian rotation curve. And when you estimate, when you take into account inclination effects, it's not as simple as it may look like. But after taking into account inclination effects, you play with your statistical analysis and you are able to estimate the mass, the central mass of the object, and you get a mass of 3 billion solar masses of some dark object at the center of this galaxy. And we do not see something shining with a luminosity corresponding to billions of stars at the center of mass of this galaxy. So something very funny is going on. We have a supermassive black hole. You cannot construct a stable system with 10 to the 9 solar masses with a size of 1 parsec or a couple of light years, okay? The system will very quickly collapse and produce a black hole. So this is an indirect argument that whenever you see a compact mass with such a huge mass in a tiny region, it must be a black hole, okay? And we do not have strong reasons to consider exotic objects like gravastars, boson stars, you name it. I'm sure there are other exotic stars, exotic objects that people thought about, but we do not have empirical evidence to think there is something exotic like these objects at the centers of galaxies. Perhaps there is. Let's keep our minds open. But I'm not excited about the prospect of having exotic objects in the centers of galaxies. Here is another result. This is now for the galaxy NGC 4258. Here, again, you see beautiful Keplerian rotation curve. Now you estimate the central mass, and you get a mass of around 30 million solar masses for the central hole of NGC 4258. This was a very important Nature paper in the mid-90s by Miyoshi, where he obtained this. This was, I think, the second best estimate of a black hole mass at the center of our galaxy. Now we have estimated black hole masses for thousands of supermassive black holes. And the most definite proof of the existence of a black hole so far is resolving the individual orbits of stars, like the movie I showed you before. This is a 3D model for the orbits of the stars around the invisible, almost invisible center of mass of our galaxy. Okay, the Sagittarius A star is located at the center of where the orbits all converge. And you can directly model the resolved observations of the stars and constrain the mass of the central black hole to be 4 million solar masses. In my opinion, this observation deserves a Nobel Prize. It's decades of observational monitoring at the center of our galaxy, and there can't be anything but a black hole if Einstein's theory is correct, with such a high mass at the center of our galaxy. Of course, we might be living in a universe with 11 or 100 dimensions, and then everything is possible, but we do not have any reason to believe so. Besides beauty, depending on what you define as beauty. So the second observational evidence that you might be looking at a black hole is if you have a strong point-like electromagnetic radiation. In other words, radio, gamma rays, and X-ray emission, the kind of a strong point-like emission that you cannot produce easily with stars or other more mundane astrophysical phenomena. What we call this non-stellar continuum in astronomy. And if you are seeing from a system strong radio or strong gamma rays or strong X-rays, you might be observing the manifestation of an accreting black hole. And it's the more observations in different wavelengths you have of the system, the better. Because with more observations, you can construct what we call the spectral energy distribution of the system and directly test ideas about black hole accretion. This is one example. This is the spectral energy distribution for comparing the electromagnetic spectra of what we call quasars. Quasar is a kind of active galactic nuclei compared to a more normal galactic center. And you can see the black line shows the typical spectra of a more normal galaxy. And if you look here to the right side of this plot, at the 10 keV, if you look at the upper part of the plot, at 10 keV frequencies, you see that the quasars emit a lot of X-rays. The luminosity on the y-axis is much higher for quasars compared to more normal galaxies, like what we call starburst galaxies. So this is the evidence for X-ray emission being produced in the accretion disk. Also, if you look at the red curve here, the radio wavelengths between 10 centimeters and 1 millimeter, there is way more radio emission coming from the quasar than from the normal galaxy. So that's emission probably from regions with a high magnetic field with relativistic electrons, synchrotron emission. This is another example of the manifestation of a black hole at the centers of galaxies. This kind of system we call Blazars. And a blazar is producing a relativistic jet. And by chance, we are looking at the beam of the relativistic jet, okay? So we are seeing the effects of special relativistic aberration and Doppler shifting. And if you take a spectrum of these blobs of material being produced by the jet of a supermassive black hole, and you are looking at the beam of the jet, this is the spectra you get of a blazar. So you have the signatures of very strong synchrotron emission. Okay, you see the effects of synchrotron self-absorption, where the gas basically kind of absorbs its own synchrotron emission. Anyway, it's a very complex system. It's a very complex spectrum. There's a lot of rich information you can get from modeling this electromagnetic radiation. The third signpost that you are observing a black hole is if you observe broad emission lines. So spectroscopy is really important if you want to catch black holes in the act. So this is what I'm talking about. The bottom plot shows a spectra plot. You have x-axis wavelengths, the y-axis is the intensity, and you see some emission lines. They look almost like direct deltas, okay? Here, the bottom spectra, you don't have a black hole. You have ionized gas, okay, which is freely floating. There is essentially no gravity, and there is very little motion of the gas, so you almost get direct deltas located at the energy transition, the wavelengths corresponding to the energy transitions of electrons in different nuclei. Now, if you put a black hole there, the black hole will start making the thing. You put black hole and you put an angular momentum in the gas. What happens is the gas will start orbiting around the black hole. Speeds will increase dramatically, and by Doppler shifting the emission lines, an emission line that was a direct delta will be broadened by the motion, by the orbital motion of the gas. And this is what happens when you observe the spectrum of the system. Let's look in particular at the hydrogen emission line, which is the one around 6,600 angstroms. Can you see that the upper two spectra, they have broader emission lines. They are not direct deltas anymore. You can model them with more complicated Gaussians, but they got broadened because the gas is moving faster. Okay, so when you put a supermassive black hole surrounded by ionized gas emitting emission lines at the center of a galaxy, the typical velocity dispersions that you get is bigger than a couple thousand kilometers per second. So you have broad emission lines, and this is another telltale of the presence of an accreting black hole. And finally, if you have strong optical emission lines, also you are probably dealing with an accreting black hole. So you see, we do not need gravitational waves to probe black holes. Okay, you can use electromagnetic radiation to advance our understanding of black hole physics. So this is, I will not talk much about this plot. It's a bit complicated, but this is called something that astronomers call diagnostic diagram. And the idea here is that it takes a couple of emission lines in the optical, the O3, some transition in the electrons in the oxygen element, in the hydrogen element, and in the nitrogen element. And then you make this plot of the ratios of these emission lines, and you can build this kind of a diagnostic diagram which tells you if the spectrum ionizing the gas, where is it coming from? Is it due to young stars ionizing the gas, or is it due to the typical spectrum produced by accretion onto a black hole? So this is a very indirect way of characterizing your central supermassive black hole, but it's a very important observational result. And finally, I will not talk much about this, but if you see superluminal motion on the sky, you probably are dealing with a black hole, okay? I can talk more about superluminal motion after the lecture. We commonly observe superluminal motions in different parts of the sky, okay? And you may ask yourselves, okay, but we cannot go at the speed of light. What is going on? We observe superluminal motion on the sky. And usually when we see superluminal motion, we are dealing with black holes producing a relativistic jet. So let's talk now about active galactic nuclei, AGNs, a bit more about these AGNs. So we are surrounded by active galactic nuclei in all directions of the sky. On the upper left, in any wavelength that you make, if you look at sources on the sky in any wavelength, usually your sky will be dominated by point sources, which are accreting black holes. And this is true for X-ray emission, this is true for optical emission, this is true for gamma ray emission. Each point you see in each of these mole-wide projections of the celestial sphere corresponds to a supermassive black hole on the sky. So over the years, by observing this radiation from active galactic nuclei, astronomers, they figured out, much like this was kind of a random study and trying to make sense of the observations of AGNs, astronomers essentially converged to a picture where there are three main observational properties which separate an AGN. So if you observe an accreting black hole at the center of a galaxy, these are the three main observed properties. And the radio power, the z-axis, the amount of radio emission this object is releasing. This is a very phenomenological study, a painstaking work that took decades to come to this phenomenological understanding of active galactic nuclei. So first of all, some AGNs like to produce radio emission, some of them don't. Also, some AGNs, they like to produce broad or narrow line emissions. And some the AGNs also, they have dramatic different levels of luminosity from the centers of galaxies. So let's start by thinking about what really means this broad narrow line classification of AGNs. So if an AGN has broad lines, astronomers decided it's really terrible. Astronomers, they like to call things type 1 and type 2, okay? So type 1, they saw AGNs with broad lines and AGNs without broad lines. So of course, type 1 with broad lines, type 2 without AGNs, without broad lines. There are also type 1 and type 2 supernovas, type 1 and type 2. There are many things that they call type 1, type 2, unfortunately. Here, type 1 with broad lines, type 2 without broad lines. This is, on the upper side, you see a type 1 AGN with the typical broadened lines. On the bottom panel, you see an AGN with more narrow lines. Roughly half of AGNs, they do not show broad lines. They have only narrower lines. And the breakthrough in this field was the realization that when you look in polarized light, the type 2 AGNs, they also have broad polarized lines in polarized light. So we ended up converging in a picture to unify this phenomenology of with or without broad lines, where we basically think that there is a donut of dust circling many black holes, many supermassive black holes. And depending on the line of sight of the observer with respect to this donut of dust, we call a torus of dust. If you have your dusty torus, imagine that this is a cross section of your dusty. There is some dusty torus, okay, and this is the angular momentum of this dusty torus circling around a central black hole, which has a nice accretion disk here around the black hole, okay? The thing is that the dust will prevent us from probing the emission lines of the gas accelerated near the black hole. So if you have a dusty torus around the black hole and you are looking at this line of sight, it will not see the broadened emission lines due to the relativistic motion around the black hole. So this is what we think that happens to explain. This is what we think explains the type 2 objects. The dust is blocking our line of sight, whereas if by chance the observer is looking here, he will suddenly see the broad emission lines of the relativistic gas around the black hole, okay? So this is what they call the unified model of AGNs, but it really is only an orientation explanation of the difference between the presence or not of broad emission lines around supermassive black holes. Now let's talk about the z-axis of this plot, which is the radio classification. Radio weak objects, radio weak AGNs, we call radio quiet ones. Radio strong, we call radio loud ones. And we quickly converge to this picture where the AGNs which are not emitting strong radio emission, they probably don't have strong magnetic fields, and they don't have a lot of synchrotron emission, so therefore they don't have jets, whereas the radio loud ones probably have strong jets producing synchrotron radiation. And quickly astronomers realized that only 10% of supermassive black holes, they have jets and they are radio loud. So for some reason, whenever you produce a supermassive black hole in the universe, only 10% of your supermassive active black holes, they are producing jets, and we don't really understand why this number, this fraction of 10%. And this must be related to the Kerr metric, to the spin parameter of the Kerr metric. We have some ideas, but we are not sure. And finally, the nuclear luminosity, how luminous is an active galactic nucleus. We have very feeble AGNs that we call low luminosity AGNs in the centers of nearby galaxies. They are very weakly accreting. They have low luminosities. And on the other hand, we have the quasars, which have huge luminosities. Okay, so we have this challenge now of trying to account for these three observed properties of AGNs with a nice, concise theoretical picture. You are a theorist. What do you do to understand the variance in the properties of active galactic nuclei? The first realization, as I mentioned, was that the first parameter to understand the system is the inclination of the observer, if your line of sight is intercepting the dusty torus or not. So the first parameter is the orientation. It explains the difference between broad and narrow lines. The nuclear luminosity is explained by the accretion rate of the accretion disk in the supermassive black hole. The third axis is a bit more complicated, but we think that black hole spin, the spin parameter of the Kerr metric, is related to the difference in the radio power, and there is a suspicion that the magnetic flux also is involved. There are many issues with this. So this is a proposal for a unified theory of active galactic nuclei using only the Kerr metric and feeding the Kerr space-time with baryons and also leptons, electrons. Okay, so this is the simplest picture so far that we have of how a black hole behaves in the center of a galaxy. There are many issues with this AGN unification proposal. I will skip some. I will just mention briefly one of them. That we have been able to estimate the Kerr spin parameter for many supermassive black holes. Here is the normalized spin A over M for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, about 15 AGNs. And you can see that this is very interesting. You can see that the spins, they are clustering around the maximum spin here. For lower mass black holes, they seem to have higher spins. The more massive ones, they have more average black hole spins. What is puzzling here is that none of these estimates of black hole spin, none of the objects which have high black hole spins, they produce jets. Okay, so is this pointing out that the Blandford-Snellius process is wrong in some sense or incomplete? We don't know. We don't know. But the black hole spin is not the only parameter here regulating this activity of these black holes. Okay, now I will go to X-ray binaries. X-ray binaries, some of the phenomenology. This is the structure of an X-ray binary. The more massive accreting object surrounded by a less massive one. These are some of the X-ray binaries that we discovered so far. It is incomplete. It's missing a couple of X-ray binaries. What you are seeing here is the actual physical proportions of the accretion disk around the black hole and the actual scale of the companion star. And astronomers realize that the X-ray spectra of the systems is very different. And we quickly converge to a scenario where the different types of spectra and the different shapes of the X-ray spectra are related to the different states of the accreting material around the black hole. So we have what we call a thermal. We have what we call a thermal state, where there is a black body-like emission in the X-ray spectrum, which is probably due to the thin accretion disk, so the green line. We also said it's very complicated, actually, the phenomenology of X-ray binaries, reflecting the complicated physics in the accretion disk. It's not only space-time. You have to take into account the fluid dynamics, the magnetohydrodynamics around the black hole. There is an intermediate state. There is what we call a hard state, hard because we classify spectra in terms of soft or hard, depending on the inclination, the number of ionizing photons you have on your spectrum. The hard state, we think there is a radiatively inefficient accretion disk that explains the hard state of X-ray binaries. And now I will show you an animation which reveals a bit of the complexity when you have the fluids, magnetized fluids, radiating around a black hole. What you'll see here is what we call a hardness-intensity diagram. On the y-axis, it's the X-ray luminosity of the system. On the x-axis is the shape of the spectrum, the inclination of the spectrum, we call hardness. And here you will see more or less 3 weeks in the life of one stellar mass black hole in a binary system, GRS 1915, very important X-ray binary. So pay attention now. This is basically the evolution of the system over about 20 days. And pay attention to what we think is happening to the accretion disk and the jets and the outflows that are being produced by the system. Pay close attention. So the system switches to a low hard state where you have a powerful jet. Then it goes to an intermediate state where the jet disappears. There is a high state where the jet disappears even further and you have strong uncollimated winds. And then the system goes back to a low hard state again with a very strong relativistic jet, okay? So this is a very complicated behavior, and this is one of the outstanding issues in black hole astrophysics that we have no clue about how to reproduce with physics this diagram, putting in a computer in a accreting black hole, letting it run with the physics we know, and reproducing this behavior of an actual stellar mass black hole, where we can catch in real time the dramatic state transitions of the gas around the black hole. So we don't really understand the nature of these state transitions and the connection between the jet that you get out of the system and the accretion disk. I will skip this, and now I will talk a bit about gamma ray bursts. So I basically mentioned already most of the main elements of our paradigm for gamma ray bursts. There are two types of gamma ray bursts. There will be a presentation about gamma ray bursts next week. So stay tuned for the lecture by Sylvia Zhu. Sylvia will will tell you way more about gamma ray bursts, even for more information about gamma ray bursts. So there are two types of gamma ray bursts. There are the long ones, which what is a gamma ray burst? They were discovered because astronomers, they were looking at this funny source in the sky, and in many cases with X-ray and gamma ray telescopes, when you look at a gamma ray burst and you plot the evolution of the brightness of the gamma ray burst, it's going quiet, and all of a sudden, and then it disappears. And the duration of this pulse of gamma rays and hard X-rays, the duration was used to classify the kind of gamma ray burst into two kinds. So the long ones, they have they have durations higher than 2 seconds approximately, and the short ones, they have durations less than 2 seconds and sometimes milliseconds. So our picture for long duration gamma ray bursts is that they are coming from the collapse of massive stars, the collapsers, where there is a core collapse, as I mentioned before, and you get a relativistic jet. The short continue talking a little bit about the long gamma ray bursts. The physics is very complex here because, okay, so the jet, the new jet punches a hole in the star and it keeps propagating. So imagine that you have a star here and then the star core collapses, produces a new black hole, produces an ultra-relativistic jet, and the jet very quickly destroys part of the star and keeps flowing outside the star, okay? So eventually this jet will, if there are some winds or some material that was ejected during the evolution of the star from in previous times, eventually this jet will collide with this material, okay, and produce shock waves because it will create discontinuities between this slow moving gas and the relativistic gas here. So we think when we look at the light curves of these long GRBs, we see all sorts of electromagnetic radiation being produced by the gamma ray burst. We see gamma rays, which is what we call the prompt emission. We usually see this burst in gamma rays. And a couple of hours later, we see a couple of minutes or a couple of hours, usually a couple of hours later, we see following the gamma rays, we see radio emission, optical emission, and X-ray emission. It's very complicated, okay? This is a whole business of astronomers dedicated to monitor gamma ray bursts in the sky. I have many colleagues at NASA that they and other institutes around the world, and now I think many people in LIGO are probably also doing this, where they have their cell phone, it turns on whenever there is a gamma ray burst exploding in the sky, okay? I have a friend of mine who, because of this, got a Nature paper almost for free. She found, not for free of course, but she found a couple. This was many years ago. She found the farthest gamma ray burst. She was on duty, and then I think that she was sleeping, and she got the beeping from the cell phone woke her up. She did the monitoring, the observation, that it was the farthest gamma ray burst at the time, and she got a first author Nature paper out of this observation. This is not uncommon for GRB people, for gamma ray burst people, gamma ray burst astronomers. So this is what the light curve looks like. First, you have what we call the prompt emission, which is when probably the jet is destroying parts of the star and producing a shock, non-thermal electrons. So you have the prompt emission. A couple of hours later, the blast wave of the jet it's expanding. It collides with material around the star, and you produce another glow called afterglow, which shines in radio, optical, and X-rays. And if you put simple models of how this jet collides with material and is decelerating as it collides with more material, you can build models for this blast wave using the physics of shock waves, and you can constrain the energetics of the jet, you can constrain the collimation of the jet. There's a very rich information you can obtain from this. The same goes for short gamma ray bursts, but in short gamma ray bursts, it's not only one star that gives rise to your jet. You have a binary system. Then you also produce jet, and once the jet breaks out, it will eventually also collide with material around the star. And then the novelty for jets producing neutron star collisions is that not only you have a jet, but you also have an uncollimated ejecta. Due to the tidal forces in the neutron star collision, you will have some last collimated ejecta being shown in red here. And the interesting thing is that whereas the jet produces radio, optical, X-rays, and gamma rays, this material shown in red is very rich in neutrons. And then the neutrons will suffer this process called rapid capture of neutrons, which I think was proposed by Fermi a long time ago. And eventually you will have the conditions in this ejecting material to produce heavy elements in the periodic table. And the radioactive glow of the neutrons, which are producing new heavy elements that we call lanthanides, if you are lucky, you can catch this glow in infrared, optical, and UV. So we believe that mergers of neutron stars, they produce this ejecta, they produce lots of heavy elements, lanthanides, and they might be responsible for most of the lanthanides that we have on Earth, including if you have gold. All of you have some amount of gold right now with you in the circuits of your cell phones, okay? Gold is a very good conductor. Probably this gold was produced in a neutron star collision a couple of a billion years ago in the surroundings of the solar system. I have a ring here which has some gold. Probably this watch has some gold from a neutron star collision. Sylvia Azul will tell you more about the physics, I hope, the physics of what we call kilonovas next week. The person who made a model for the evolution, that he predicted the kilonova glow only 10 years ago. It was his PhD thesis. His name is Brian Metzger. He got the breakthrough prize a couple of weeks ago. This prize set up by millionaires, the Yuri Milner and Mark Zuckerberg. They give every year a prize to physicists and astrophysicists. LIGO got the breakthrough prize, I think 1 or 2 years ago, more than $1 million. Metzger got the junior prize for predicting the kilonova physics. And he got in his bank account $100,000, which is a good amount of money. It's a typical NASA grant. Right, so I will skip this. This is a sort of a complicated, not entirely skip it, but this is a sort of complicated plot showing you the gravitational waves from the coalescing neutron stars on the bottom part of the panel, showing you the different stages that you have been learning with the analytical lectures last week and this week, the SHERP, the different stages, the coalescence. But you also have the electromagnetic signal, the X-ray or radio precursor as the neutron stars get close to each other. The short GRB, when you produce a jet, and the jet is screaming the prompt emission of a short gamma ray burst. The X-ray extended and radio extended emission as the jet punches, as the jet collides with material far away, producing shocked electrons from the collision. And then the kilonova emission, producing lanthanides in UV, and then evolving blue, red, and finally radio. So you saw this plot yesterday. Sasha showed this plot yesterday, but I will repeat it. This is the great discovery that was the birth of multi-messenger astronomy. On the upper panel, the gamma ray burst observed, the jet observed by the Fermi-Lat telescope, and on the lower panel, the the frequency plot of the gravitational wave signal from the coalescence of the neutron star. So the neutron stars coalescing, losing orbital energy, they finally coalesce entirely, produce a jet, which emits the prompt emission observed with Fermi. This is a numerical simulation of the ejecta that I told you about, the kilonova ejecta. So here, well, at the center of that plot, the evolving plot, you have the newborn black hole, and what you are seeing here is an expanding cloud of neutron-rich material, which are the R process is happening in this cloud of neutrons, and you are producing lighter elements and heavier elements, and you can build models for how this cloud evolves and cools down, and you can predict abundances of lanthanides produced. You can compare your observations and models with different cloud of neutrons to your observations and constrain the sites of production of heavy elements. Finally, now you are all experts in black hole phenomenology. Now you know what a black hole looks like, not only in gravitational waves, but electromagnetic radiation, if you have been paying attention to the lectures. And now we'll give a few final words about unifying all black holes in the universe. Of course, Einstein unifies all black holes. But what about the physics of the accreting material? So we have strong reasons to believe that the black hole physics and the black hole accretion process should be an universal process, scale-free essentially. The scale of the system is dictated by the mass. But look, the physics is the same. If you have a m equal 10 solar masses or m equal 10 billion solar masses, the physics should be very similar. Of course, the scale is a bit different, but the phenomenon should be scale-free and universal. And we are starting to build a picture where we are realizing that the observations we see in black hole binaries, AGNs, and gamma ray bursts, they are all connected and they all can be unified. And there should be simple phenomenological laws guiding us in how to connect the properties of the matrix and the fluids to the observations. I myself contributed a bit to this game. This is a result that I published in Science this is a bit old now, 6 years old. So we found out this was a kind of not entirely accidental discovery. But I found out that the jets produced in Blazars, they follow a very simple scaling that you can connect with the energetics of the jets produced in gamma ray bursts. Okay, so this is so it seems like black holes, they are more, when you find the right way of depicting the observations, black holes are very simple. They are scale free. And the important lesson from this result is that you can do effectively knowledge transfer. You can learn things looking at a small size black hole, and you see things happening on a matter of a couple of days or minutes or weeks. And you can take the knowledge you learn from a small black hole and transfer to understand the supermassive ones, which evolve on time scales much longer than the typical life scale of a graduate student, okay? And then you can make projects for graduate students to make actual discoveries within the lifetime of a PhD thesis, okay? So the most promising objects for doing this kind of quick studies, of course, is the lighter systems. And so we finished the lecture on phenomenology. And these are the regimes now to finish the lecture. These are the different regimes of black hole accretion. Y-axis, the logarithm of the accretion rate on the accretion disk. The x-axis is the logarithm of the radius of the system. And here you see the different regimes of accretion and the different kinds of systems they explain. Low accretion rates, you have low velocity AGNs, faint X-ray binaries. Close to Eddington accretion rates, you have brighter X-ray binaries, quasars, and Seyferts. And higher accretion rates, you have tidal disruption events and active galactic nuclei, and even further gamma ray bursts and supernova even. Okay, so this is how we unify all black hole physics. There are many questions here in this quest to understand how black holes occur in nature. Next week, multi-massive with Sylvia. The two lectures will be multi-messenger astronomy and gamma ray bursts and other lectures. And finally, a summary of everything we saw about black hole astrophysics. So black holes, they are collapsed objects. Light cannot escape black holes, but you can see light not from inside the event horizon, but from the radiating matter spiraling towards the event horizon. These systems, they are fantastic laboratories to probe the conditions of matter in extreme environments, in extreme curvature that we do not have access here on Earth, okay? So they are very fascinating. They produce the brightest systems in the universe. Quasars and gamma ray bursts are byproducts of black hole accretion. They not only accrete matter, but they produce powerful outflows in the form of relativistic jets. These jets can be very important for galaxy evolution, something that I didn't really mention, but the black holes can affect the lives of the galaxies they inhabit. And they are also the most powerful particle accelerators in the universe. I will make the slides available on the website I showed in the first lecture. And now I would like to finish with a advertising for my institute and for the University of São Paulo. So you are very welcome. I'm aware that many, perhaps most of you are not coming from Brazil. You are very welcome over the next week to come visit University of São Paulo, the Instituto de Astronomia, Geofísica e Ciências Atmosféricas da USP. We have about 30 professors, we have about 30 postdocs, we have a lot of graduate students locked in our dungeons. Oh, I'm kidding. And we are investigating of course, the deepest questions: the origin of the universe, the origin of stars, the evolution of black holes, cosmology, and also instrumentation. My group is the black hole group. You can have more information about our group in this website, blackholegroup.org. The goal of the black hole group is to investigate and advance the understanding of black hole astrophysics, all the topics I mentioned so far to you. We are particularly interested in the black holes at the centers of galaxies, like this beautiful radio galaxy M87, but also the black hole at the center of our own galaxy. There are opportunities for graduate studies in our group in observations. More or less half of the group is doing phenomenology, doing gamma ray observations and optical observations of black holes. And we are also doing theory, and by theory I mean mostly numerical simulations of accretion of gas onto black holes. I am also very excited in using GPUs. I can tell you afterwards. Come talk to me if you are interested in working in any of these topics, and if you want to learn what is a GPU. All of you have GPUs in your cell phones. If you play games, you have GPUs also at home. They can be very powerful to accelerate science. We are using, my group is using the Fermi-Lat Gamma Ray Observatory on space. My apologies, the slides are in Portuguese. We are using the Fermi-Lat Observatory on space to advance the understanding of black hole astrophysics, more specifically particle acceleration in jets. In the future, the Cherenkov Telescope Array, which will take a long time yet to start getting results, but I am interested in the CTA. And this is the laboratory that we are using, the entire sky. We have observations of gamma rays with Fermi of the entire sky. And right now, one of my students who is not here, he's busy in his office analyzing gamma ray observations of the black hole at the center of our galaxy, which is producing this funny bubble shape. This, do you see it looks like a bubble emanated. This is the disk of the galaxy horizontally, and vertically it looks like there is some kind of hourglass shaped structure. So Fabio is analyzing this black hole in gamma rays. The simulations we are doing, hydrodynamic and MHD simulations of accretion onto black holes. I am particularly interested in understanding the kind of light you get out of this system to compare with observations. This is the group right now. Two of them are here, and you get points if you identify them where they are. Advise they are sitting at the back of the room. So they go ask them about the projects they are doing. So there are really a lot of science, a lot of exciting stuff happening in our group right now. If you want to apply for graduate school in USP, I have this advertising slide. Physics student, come do your master's or PhD in astrophysics at IAG-USP. There are two, if you want to do a master's or direct PhD, you can apply in October, November, and May, June If you finish your master's, you can do a PhD. All year long, you can apply for a PhD if you have a master's. You need to do an exam, a unified exam of physics. We call it Exame Unificado da Física, EUF. You need to provide us your CV and 2 letters of recommendation. If you are a very good student and you have outstanding grades, you can apply for a FAPESP scholarship. They are prestigious scholarships. Only the best students get the FAPESP scholarships. The cool thing is that the salary goes up slightly over the time of your course. So FAPESP scholarships are only for the best ones. So if you are interested in doing work or this, if any of these topics is of interest to you, come talk to me. I'm very happy to talk with students and also people interested in doing postdocs. Thank you very much. Questions? I know that I can feel the energy level of the room is low. Like it was affecting me during my lecture, looking like, oh, the one guy was like, oh, is my lecture so boring? I'm gonna cry here. But questions, if your energy level allows. If no, yes.
I was wondering if all your work that you group is with simulations, or you also do analytical simulations?
Right now, it's mostly simulations. In the past, I did some work on analytical calculations, more specifically analytical calculations of the spectrum around the disk, and also for the Penrose process in Kerr black holes. I have a lot of ideas for analytical calculations and projects based on analytical calculations, but I don't have the time myself to do them. So I'm looking for bright people to implement calculations. But right now, we are focused on numerical simulations, but there is room for people doing analytical calculations.
Yeah, because my second question was,
Yeah.
this analytical approach is still valid in some sense if you have the machinery.
Oh, we are talking now philosophical. We are talking philosophy, more or less. While we talk final slide of my lecture. Look, it doesn't help you if you do a very fancy evolution of the nonlinear MHD simulations and you don't have a basic understanding of the analytical results, right? When you set up a numerical simulation, it's a virtual laboratory. It's really an experiment. You do the simulation, you wait a couple of days, depending on the kind of cluster you're using, depending on the kind of simulation. It spits out arrays of numbers. It doesn't give you the laws of physics. It doesn't give you have to figure out, you really have to analyze the data for a virtual universe to really try to figure out what is happening there, okay? So in some sense, it's quite complicated to analyze these observations. But sometimes the basic physics is very simple and analytical, you know. So of course there is a lot of room for analytical understanding of what is going on. The most complicated things will require numerical simulations to deal with the nonlinearities, but you always can find regimes where you can explain something with some linear approximation. So there is room for analytical calculations. Let me see if I can come up with a concrete example of something I'm curious on. Okay, so one thing I'm curious about for accreting black holes, what is the critical limit at which you have a relativistic jet or not? Okay, is there a critical spin? Is there some critical parameters where you can have a radio loud AGN or a radio quiet AGN? I think this can be done analytically. You don't need to do. If you had to do numerical simulations, you will spend your whole time doing simulations because they are very expensive computationally. This is one calculation that I think is possible to do analytically, like this threshold for jet production. I can think more about other more specific things. Yeah. So I'm not sure I answer your question, but yeah. Any more questions? Yeah.
Is there any effect of dark matter, let's say supermassive black accretion in this?
Okay, so the question is there any effect or connection between dark matter and these supermassive black holes sitting at the bottom of the potential wells in galaxies? The answer is a sound no. Okay, okay, probably no, but very probably no. Why? Because it's very, according to the usual picture, you cannot cool dark matter, okay? So dark matter does not cool dark matter particle. If it's something like a WIMP, it's very hard to cool a dark matter particle. But you need to cool down these guys for them to collapse, and then you drag them to the black hole and form an accretion disk, okay? And you will not be able to drag most of dark matter. If the dark matter gets in the event horizon, it will be accreted and it will contribute to the mass of the black hole. And probably, of course, there is some if you could do a histogram of how much dark matter is inside a black hole, there is some dark matter there, okay? But so this is the thing, it's very hard to have significant amounts of dark matter getting in the accretion disk and getting down to the event horizon because it's hard to cool down and make it collapse, number one. And number two, at the very centers of galaxies, the central regions of galaxies, there is much more baryons than dark matter. So if you go and you look at the galaxy integrated, of course, there is a lot of dark matter, almost 10 times more dark matter than the normal elements from the standard model of physics. But at the central region within one light year, a couple of light years where you have the black hole and its gravitational region of influence, there are, you can do this calculation with different model, cusp model or core model, but there is 1,000,000 times more density in baryons than dark matter, okay? So the dark matter is just a small perturbation to the mass of the black hole, okay? Did I answer your question? So now, two things. The density is very low near the black hole of dark matter. And number two, the dark matter cannot collapse and be accreted down to the black hole. Some particles will eventually go around and fall inside, but very little. I will give you even a number. I will say that it's 10 to the minus, I have to do this calculation, but probably 10 to the minus 6, a fraction of 10 to the minus 6 of the mass of the black hole is dark matter, if you want a number. But I will do the calculation. Any more questions? Yes?
One comment. You mentioned the Sagittarius, maybe Scorpio, but not Archer. Those two figures that are correlation. That one was Scorpio. The right top one was this Archer. Sagittarius was Greek or Archer.
Sagittarius mean what? Ah, Archer. Really? Whoa. Okay, thank you. Thank you. Today I learned that Sagittarius is Archer. Good to know. Thank you. So no more questions? Questions from there? No? Okay, so thank you very much. So what's the plan now? Should we finish the school, or there will be a hands-on?
I go to the airport.
Okay. Do you want to say some final words to the students before they leave? Or you said already?
Well, I think the plan is we're gonna have a coffee break. Okay. Do you want to do an interesting thing afterwards, or?
Ah, yes. Okay. So there is something I forgot. But it depends on the interest of the students. Okay, do you want to? I I would be tired of hearing myself because they heard me already for almost 6 hours. So, but if you are interested, it depends. I can talk half an hour about the Event Horizon Telescope, which I forgot. So let me judge here the interest of. Sorry. Who wants to listen half more hour about another half an hour? Not now, after the coffee break, about the Event Horizon Telescope. Can you raise your hands? Don't be. Okay. Okay. Okay, so after the coffee break, Event Horizon Telescope, okay?
Well, I think for me,